Welcome to the deep dive. Today, we're going to be looking at some physics textbooks, and we're going to be exploring heat and temperature.
Yeah.
I think most people, when they think of heat and temperature, they think they've got it down right.
Yeah, I think
Like,
so.
we all experience hot and cold every day, but
Yeah.
yeah,
You know, like, it's one of those things where it's kind of deceptively, like we use the terms all the time,
exactly.
but when you really start digging into the actual definitions, the physics of it, it can get kind of interesting
Yeah.
pretty
Okay.
fast.
So in this deep dive, we're going to try to challenge some assumptions
Hmm.
and uncover some cool facts about heat and temperature. Like, for instance, did you know that there's a type of heat transfer that doesn't even involve a change in temperature?
Right. Yeah, that always blows my mind a little bit.
Yeah, and I think we're going to get into absolute zero,
Uh-huh.
too. And, the fact that it's impossible to reach,
Right.
which is also crazy.
Hmm.
So let's start with the basics.
Yeah.
Heat, right. So our textbook here defines heat as the flow of energy from a hotter object to a colder one
Right.
because of a difference in temperature. So it's kind of like, if you picture water flowing downhill, it always goes from higher to lower.
Yeah, that's a good analogy, but what's really key here is that heat's not something that an object has.
Okay.
It's not a substance.
Right.
It's not like, I've got some heat in my hand.
Right.
Like,
So it's more about the movement,
it's the action.
the energy transfer.
Exactly.
Okay.
It's energy in transit. So it's the process of the energy transfer.
Okay, so that's heat and it's this energy transfer. What about temperature then?
Right. So that's where, it gets kind of tricky because they're obviously related.
Right, they're definitely connected.
Yeah, very intimately connected. But they're not the same thing.
Mm.
And I think a good way to think about temperature is that it's a measure of the average kinetic energy of the molecules in a substance.
Okay, hold on. You're saying kinetic energy. So, are we talking about the molecules are they, moving around
Yeah.
inside the object?
Yeah, so think of it as I don't know, the molecules are having this crazy dance party
Okay.
inside whatever object you're talking about.
Right.
And so the faster they're moving, vibrating, rotating, bumping into each other, the higher the temperature.
Okay, so it's like a measure of how much they're, grooving.
Yeah, exactly. Exactly.
But here's the thing. You said it's the average kinetic energy.
Right.
So that means temperature isn't about the total amount of heat energy in an object.
Right. And that's where I think it gets kind of counterintuitive
Right.
for a lot of people.
Right.
Because it feels like, okay, well, if something's hotter, it must have more heat.
Right.
But that's not necessarily true.
Mm-hmm.
So, for example, you could imagine a bathtub full of lukewarm water
Okay.
versus a cup of boiling water.
All right.
Right. So the cup of boiling water obviously has a higher temperature.
Yeah.
You wouldn't want to jump in a bathtub of boiling water.
No, definitely not.
But the bathtub, even though it's cooler, actually contains more heat energy overall because it's got so much more water.
Wow. Okay, so you're telling me that my lukewarm bath
Yeah.
actually has more heat energy than a cup of boiling water, even though the boiling water could, scald me.
That's exactly right.
That's crazy.
Yeah, and it just goes to show that, temperature and heat are related, but they're not the same thing.
Okay, so let me see if I got this straight.
Yeah.
Temperature is like the average intensity of that molecular dance party.
Right.
And heat refers to the actual transfer of thermal energy.
Exactly.
Yeah, you got it.
Okay, all right. I think I'm starting to get it.
Yeah.
Now, let's talk about, how this heat actually gets around.
Right.
So back in school, I learned about conduction, convection, and radiation. Are those still the main ways heat can travel?
Absolutely. Yeah.
Okay, good,
Yeah.
good. I'm glad some things haven't changed.
Yeah, some things stay constant.
So let's break them down one by one. What's conduction again? So conduction is heat transfer through direct contact. So if you touch a hot stove, for example, ouch.
Oh, yeah, I've done that one too many times.
Right, you feel that heat instantly, and that's conduction.
Okay, so that's conduction. What about convection?
Convection is all about heat transfer through the movement of fluids.
Fluids. So we're talking about liquids and gases.
Exactly. So think about boiling water. The water at the bottom heats up, and it becomes less dense, so it rises, and then the cooler water sinks, creating the cycle.
Oh, yeah. Yeah, those convection currents.
Exactly. And that's how heat gets distributed throughout the pot.
Okay, so conduction is direct contact. Convection is all about these fluid flows. And then there's radiation. That one always seemed a little mysterious to me.
Yeah, radiation is a little bit different because it doesn't need a medium to travel.
Okay.
So, It's how we feel the warmth of the sun, even though it's millions of miles away through the vacuum of space.
Right.
So it's heat transfer by electromagnetic waves.
So like little invisible packets of heat energy.
Exactly. Kind of like little messengers delivering warmth at the speed of light.
That's amazing. But this whole idea of heat being energy transfer,
Yeah.
I'm pretty sure that wasn't always the accepted theory, was it?
Right. No, it wasn't.
Did they used to think heat was some kind of fluid?
Yeah. For a long time, scientists believed in what was called the caloric theory.
Oh, yeah, the caloric theory. Vaguely rings a bell.
Right. So they thought heat was this invisible, weightless fluid called caloric that flowed between objects. So a hot object would be full of caloric and a cold one would have less.
Okay, I mean, that makes sense in a way, right?
Right. It seems pretty intuitive if you, hold a hot cup of coffee. It feels like something's flowing into your hand.
Yeah, you feel that warmth.
Yeah, but the caloric theory ran into problems when it couldn't explain things like, if you rub your hands together really fast, they get warm.
Right.
Where's that extra caloric coming from?
Yeah.
And also friction generating heat. So it just couldn't really account for all the observations.
Okay, so the caloric theory had some holes in it. So what happened next? Did someone come up with a better idea?
Yeah, eventually scientists realized that the caloric theory just wasn't cutting it. And they started developing what we now call the dynamic theory of heat.
The dynamic theory, okay.
Yeah.
What's that all about?
So the dynamic theory says that heat is actually a manifestation of the kinetic energy of molecules within a substance. So remember those dancing molecules we talked about?
Yeah, the molecular dance party?
Exactly. So the more they move, the hotter the substance becomes. No need for any mysterious fluid.
Okay, so it's not a substance, it's more like a form of energy.
Exactly.
Wow, so we went from invisible fluids to dancing molecules.
Yeah, it's a pretty big shift in thinking.
It's incredible how our understanding of something so fundamental can evolve over time.
Yeah, and that's the beauty of science. There's always more to learn and discover.
Well, on that note, I'm ready to dive even deeper. We've talked about heat, temperature, how they're related but not the same thing.
Mm-hmm.
We've explored those different ways heat can transfer.
Yeah, and we even busted the myth of the caloric theory, but I have a feeling we've only just scratched the surface.
Oh, we've just begun. There's so much more to explore, like how we measure temperature, from simple thermometers to the really complex instruments used in cutting-edge research.
Right, and then there's that whole absolute zero thing, which is just mind-blowing. Is it truly the ultimate chill?
It's a question that leads us to some pretty wild implications about the nature of the universe and the limits of what's possible.
Well, I'm ready to explore those limits.
All right, let's do it. So thermometers, right?
Yeah.
They seem so simple.
I mean, yeah, you just look at it and you know if you have a fever or if it's a good day to go swimming, right?
Exactly. But
I have a feeling it's more complicated than that.
yeah, there's a whole lot of history behind thermometers.
Really?
Yeah, for centuries, people really struggled to figure out how to actually measure temperature.
So how did we go from, just feeling hot or cold to having these actual temperature readings? It was a long process, a lot of, really smart people working on it.
Okay.
But some of the early attempts used air.
Air.
Yeah, like
Like the air temperature?
No, they would look at how air expanded or contracted.
Okay.
But it was really unreliable because, air pressure changes all the time.
Right.
So it wasn't very consistent. And then eventually they came up with the idea of using liquids like mercury or alcohol.
So this is like the classic mercury thermometer.
Exactly. That was a big breakthrough. And mercury especially turned out to be really good for this.
What makes mercury so special for thermometers?
Well, it's got a few things going for it. First of all, it's got what we call a low specific heat capacity.
Specific heat capacity, okay.
Which means it doesn't absorb a lot of heat from, what it's measuring.
Okay, so it doesn't mess up the reading.
Exactly.
Okay.
And it's also a good conductor of heat, so it reacts quickly to changes in temperature.
Oh, so it gives you a result fast. Okay, cool. Anything else?
Yeah, so it doesn't wet glass.
Doesn't wet glass.
Yeah, so that doesn't, stick to the inside of the tube.
Oh, right. That would mess things up.
Yeah. And, importantly, it stays a liquid over a wide range of temperatures.
Yeah.
So you can use it for a lot of different things.
Yeah.
And it's also, you can see it really well.
Easy to read, yeah.
Against the glass.
Mercury sounds like the perfect fit.
It's pretty good.
Yeah.
But, we also use other types of thermometers.
Oh, really? What else is there? I mean, I guess it makes sense.
Yeah.
Not everything can be measured with mercury, right?
Right, exactly. So, for example, there are gas thermometers.
Gas thermometers, yeah.
So they work by looking at the pressure of a gas.
Okay.
Because as the temperature goes up, the gas expands, and that increases the pressure.
So it's like a little pressure gauge that's responding to temperature.
Exactly.
And that's cool.
And then there are platinum resistance thermometers.
Platinum. Oh.
Fancy. Yeah. So they use platinum wire because its electrical resistance changes very predictably with temperature.
Okay.
So they're super accurate. We use them a lot in, science and industry where you need to be really precise.
Right. So you've got expanding liquids, gas pressure, changing electrical resistance. What other tricks do we have up our sleeves for measuring temperature?
Well, we got plenty more.
Okay, give me another one.
So there are thermocouples.
Thermocouples, all right.
They use, it's based on this principle that if you join two different metals together,
Okay.
they'll generate a voltage.
Okay.
And that voltage depends on the temperature difference between them.
That's pretty wild.
Yeah, and thermocouples are really versatile.
Okay.
You can use them for really high temperatures.
Okay.
And even in places where it's, like really harsh environments.
So like inside a volcano.
Yeah, exactly.
Wow. Okay, so we've got a whole toolkit of different thermometers, each with its own like strengths and weaknesses. How do you know which one to use?
It really depends what you're trying to measure,
Right.
what kind of temperatures you're dealing with, how accurate you need to be.
Right.
So if you're just checking your temperature at home, a simple mercury thermometer or one of those digital ones is fine.
Yeah.
But if you're monitoring the temperature of molten metal in a factory,
Mm-hmm.
you'd need something a lot more heavy duty,
Okay.
like a thermocouple.
It's amazing how much technology goes into something that seems so simple.
Yeah.
We've gone from those basic liquid in glass thermometers to these super sophisticated electronic devices.
Oh, and I almost forgot.
What?
There are also radiation pyrometers.
Radiation pyrometers, okay.
Yeah, and they can measure temperature from a distance.
From a distance, how does that work?
They detect the infrared radiation that an object emits,
Okay.
so you don't even have to touch it.
So it's like, what? The object is giving off heat and it's picking that up.
Exactly.
That's really cool. And you could use that for anything.
Yeah, it's super useful when it's either, like, dangerous.
Yeah.
Right.
Or really difficult to get close to something.
Okay, so that's perfect for, like, a furnace.
Yeah, a furnace. Or even, a star.
A star, wow.
Astronomers use these all the time.
So we've got thermometers for everything,
Mm-hmm.
from a fever to the surface of the sun.
Pretty much.
That's incredible. And it really shows how much our technology has advanced, right?
Mm-hmm.
But at the end of the day, all these different thermometers, whether they use liquids or gases or radiation, they all rely on the same idea.
Yeah,
That temperature is a measure of how much those molecules are moving around.
exactly. You got it.
It's amazing how something so, I don't know, abstract,
Mm-hmm.
like the movement of these tiny little particles we can't even see,
Yeah,
that can be harnessed to make all these different tools and technologies.
it's pretty remarkable.
Speaking of abstract concepts, I'm still thinking about absolute zero.
Yeah.
You mentioned earlier it's impossible to reach.
Yeah.
What makes it so elusive? Well, absolute zero is more than just, like, really, really cold. It's kind of a fundamental limit of the universe.
Okay.
And it's dictated by the laws of thermodynamics.
Thermodynamics.
Yeah,
That sounds complicated.
it can be, but
Okay.
the relevant one here is the third law of thermodynamics.
Churd's law. Okay.
And it basically says that you can't reach absolute zero in a finite number of steps.
So it's like a cosmic speed limit for coldness. No matter how much we try to cool something down, we can never actually get to absolute zero.
Exactly.
That's kind of frustrating.
It is a bit, yeah. Nature's kind of put a limit on how cold things can get. We can get incredibly close, like billionths of a degree away,
Wow.
but we can't actually get there.
Okay, but if we can't reach it, how do we even know it exists? How did we come up with this idea of absolute zero?
Well, it comes from our understanding of how temperature relates to the behavior of matter, and through observations and experiments.
Okay.
Scientists can see how gases behave as you cool them down. And based on that, we can kind of extrapolate and make predictions about what would happen at even lower temperatures.
So it's like drawing a line on a graph
Yeah,
and extending it beyond the data points you've actually measured.
exactly. We're using our knowledge to kind of peek into realms we can't directly observe.
That's pretty cool.
And for absolute zero, that prediction has held up really well.
Okay, so absolute zero is like the bottom of the temperature ladder.
You could say that, yeah.
But is there a top? Is there a limit to how hot things can get?
That's a great question. And to answer that, we kind of have to delve into some extreme temperatures.
All right, let's do it.
Think like the heart of a star, or even the early universe. But before we go there, I think it's worth taking a step back and talking about the different ways we measure temperature in the first place.
Ah, you mean like Celsius versus Fahrenheit?
Exactly.
Yeah, why do we have so many different ways to measure the same thing? Seems a bit confusing, doesn't it?
It can be, especially when you're trying to convert between them. But each scale has its own, like, history and its own uses.
Hmm.
So let's start with the one you're probably most familiar with.
Celsius.
Celsius. The one where water freezes at 0 degrees and boils at 100.
Yeah, that one makes sense to me.
Yeah, it's pretty straightforward. And that's a big reason why it's so widely used,
Yeah.
in science and just in everyday life
Okay.
in a lot of the world. It was developed by this Swedish astronomer, Anders Celsius,
Okay.
back in the 18th century.
Okay.
And it just caught on really quickly because it was so, like, logical and easy to use.
So Celsius is all based on water?
Well, yeah, its main reference points are.
Okay.
Right. So 0 degrees is the freezing point of water, and 100 degrees is the boiling point.
At normal pressure, right.
Yeah, at standard atmospheric pressure.
Okay, so each degree Celsius represents like 1/100th of the temperature difference between ice and boiling water.
Yeah, that's it.
That makes sense. But then there's Fahrenheit. That one's always seemed a bit more, I don't know, random to me.
Yeah, Fahrenheit has a bit of a more complicated history. It was developed by this guy, Daniel Gabriel Fahrenheit,
Okay.
in the early 1700s.
Okay.
And he didn't just use water for his reference points.
Oh, really? What did he use?
He actually used a mixture of ice, water, and ammonium chloride for 0 degrees.
Ammonium chloride.
Yeah. And then he used the human body temperature.
Human body temperature.
Yeah, but he actually got that slightly wrong
Oh.
for 96 degrees.
So it was a bit more human-centered, I guess.
You could say that.
Like, how cold does it feel to us?
Right, instead of just focusing on water.
Interesting. But why are we still using Fahrenheit in some places?
It's stuck around, mainly in the U.S.,
Okay.
even though it's not as intuitive for a lot of things as Celsius is.
Well, I'm glad we have Celsius at least to keep things simple. But
Yeah.
you mentioned the Kelvin scale earlier,
Yeah.
and you said it's really important in physics.
Hmm.
What makes it so special?
Well, Kelvin is what we call an absolute temperature scale.
Absolute temperature scale, okay.
Yeah. So it's 0 point is absolute 0,
Right.
which we were talking about before. That point where theoretically all molecular motion stops.
The ultimate chill.
Yeah, it's like the bottom of the temperature ladder. For real this time.
Okay, so Kelvin starts at absolute 0,
Mhm.
but how does it relate to Celsius? Like, do I have to do a lot of math to convert between them?
No, it's actually pretty simple. 1 degree Kelvin is the same size as 1 degree Celsius.
Okay.
The only difference is where the 0 point is.
Okay.
So 0 Kelvin is equal to minus 273.15 degrees Celsius.
So to go from Celsius to Kelvin, you just add 273.15.
That's it.
Okay, that's way easier than I thought.
Yeah, and it makes it really easy for scientists to work with both scales.
So it's like having the right tool for the job, Celsius for everyday stuff, and Kelvin for the really crazy physics stuff.
Exactly. And, there's one more temperature scale we should mention, even though it's not used as often. The Rankine scale.
Rankine. Okay, I've never even heard of that one.
That's another absolute temperature scale.
Okay.
But this one's based on Fahrenheit.
So it's like the Fahrenheit equivalent of Kelvin.
Yeah, pretty much.
Okay.
So it has the same size degrees as Fahrenheit,
Yeah.
but its 0 point is absolute 0, just like Kelvin.
So if you really like Fahrenheit, but you need to work with absolute temperatures, Rankine is your scale.
Exactly.
Okay, so we've got Celsius, Fahrenheit, Kelvin, and Rankine.
That's all of them. Yeah.
It's a lot to keep track of, but I'm starting to get why we have all these different scales,
Yeah.
It's like they each have their own purpose.
Yeah, they're just different ways of expressing the same basic thing, you know?
Right, right.
How hot or cold something is.
It's like having different languages to describe the same experience.
Exactly. And understanding these different scales, along with all those different thermometers we talked about,
Mm-hmm.
it really gives us a good framework for measuring and understanding the world around us.
Okay, so we've got our tools and our scales. What else do we need to know about heat and temperature?
Well, there's one more concept that's really important to grasp. Thermal equilibrium.
Thermal equilibrium, what's that?
So it's when two objects in contact reach the same temperature,
Okay,
and there's no more heat flowing between them.
so it's like a temperature truce.
Exactly. They've reached this balance. And this idea is really important, not just for understanding how heat flows, but also for something called the zeroth law of thermodynamics.
The zeroth law. That sounds kind of ominous.
It's not as scary as it sounds.
Okay.
And it's called the zeroth law because, well, it was actually formulated after the first and second laws.
Oh, really? So why is it zero?
Yeah, it's kind of a funny story, but they realized it was so fundamental that it had to come first.
Right.
So they called it the zeroth law.
Gotcha. Okay, so what does the zeroth law say?
Well, it states that if you have two systems and they're both in thermal equilibrium with a third system,
Okay.
then they have to be in thermal equilibrium with each other.
Okay.
It sounds obvious, but it's actually pretty profound.
Okay, I think I need an example.
Okay, so imagine you have three objects. We'll call them A, B, and C.
Okay.
If A and B are both the same temperature as C,
Okay.
meaning they're in thermal equilibrium with C,
Mm-hmm.
then A and B must also be in thermal equilibrium with each other.
So even if A and B never actually touch, if they're both the same temperature as C, they're in equilibrium with each other. It's
Exactly.
like a transitive property of temperature.
That's a great way to put it.
If A equals C and B equals C, then A must equal B.
Yeah, exactly. And this has some pretty big implications for how we measure temperature.
Really?
Yeah, because it means we can use a thermometer, like, as that third system
Okay.
to figure out if two other things are at the same temperature, even if they're not touching.
So it's like the foundation for making sure all our thermometers are like speaking the same language.
Precisely. The zeroth law is something we take for granted, but our whole system of temperature measurement relies on it.
Wow. I never realized how important that seemingly obvious idea was.
It's pretty fundamental. Yeah. Make sure that we can compare temperatures accurately.
Okay, so the zeroth law ensures our thermometers are working properly. But I'm still thinking about absolute zero and that idea that there's a limit to how cold things can get. Does that mean there's also a limit to how hot things can get?
That's a question that takes us into some pretty extreme territory.
I'm ready for it.
Okay, we're going to have to explore things like the core of stars and maybe even the very beginning of the universe.
Okay, now you're just showing off.
But before we get to those extremes, let's switch gears for a moment and revisit those different ways heat can be transferred.
You mean conduction, convection, and radiation.
Exactly. We talked about them briefly before, but there's a lot more to explore.
All right, let's dive back in.
So we've talked about a lot in this deep dive.
We really have.
I mean, we've covered, heat is this energy transfer
Yeah.
and temperature as that measure of how much the molecules are jiggling around.
Right, right.
We even went into the different scales we use, like Celsius, Fahrenheit,
Kelvin, Rankine.
Kelvin, Rankine, the whole gang.
Whole gang's here.
And then, we even uncovered the zeroth law of thermodynamics.
The zeroth law, that was a good one. I never realized how important that was.
Yeah, it's kind of a hidden gem of the physics world.
I feel like my understanding of heat and temperature has just been completely flipped on its head.
That's what we like to hear.
I'll never look at a boiling pot of water the same way again.
All about those convection currents, right?
Exactly. But speaking of which, we were just talking about those different ways heat can be transferred.
Conduction, convection, radiation.
Yeah, and I know we touched on them earlier, but I feel like there's still more to unpack there.
Oh, absolutely. Each of those methods has its own little quirks, and they all play a huge role in how the world works.
Okay, so let's break them down one by one. Let's start with conduction, because that one always seemed the most straightforward to me. You touch something hot, you get burned.
Yeah, conduction is all about direct contact. The heat transfers from one object to another because they're physically touching. So like that metal spoon in a hot cup of tea.
Yeah, the spoon gets hot too.
Exactly. The heat energy from the tea is literally flowing into the spoon.
Because the molecules are bumping into each other.
Yeah, so the molecules in the hot tea, they're moving really fast.
Okay.
And they bump into the molecules in the spoon, which are moving slower.
Right.
And that makes the spoon molecules speed up, which makes the spoon hotter.
So it's like a chain reaction of these tiny little collisions.
Yeah, exactly.
Wow. And does the speed of that, like how fast the heat transfers, depend on what the objects are made of?
Yeah, definitely. Some materials are better conductors than others.
So like a metal spoon will heat up faster than a wooden spoon.
Exactly, because metals are much better conductors of heat.
Okay. What makes metals so good at conducting heat?
Well, it has to do with their structure. Metals have these electrons that are kind of loosely bound,
Electrons.
so they can easily transfer energy throughout the material,
Got it.
which is why metals are also good conductors of electricity.
Oh, right, right. Okay, that makes sense.
Yeah, it's all connected.
It's making me think about all those times I've grabbed a hot pot handle without thinking.
Ouch, yeah.
Metal is a harsh reminder of how good it is at conducting heat.
A quick lesson in conduction.
Exactly. But conduction isn't just in solids, right?
Nope, it can happen in liquids and gases too. It's just not as efficient.
So, like, the air around a hot object will heat up through conduction.
Exactly. But air isn't a very good conductor. That's where convection comes in.
Ah, convection, the one about fluids moving around.
You got it. Convection's all about the bulk movement of, hotter and colder fluids.
Yeah.
So think about that pot of boiling water again.
Okay, yeah. The water at the bottom gets hot,
Right. And as it heats up, it becomes less dense.
less dense. Oh,
So it rises to the top.
okay.
And then the cooler water at the top, it's denser, so it sinks to the bottom.
So it's like this constant cycle of the hot water rising and the cold water sinking.
Exactly. And those are the convection currents.
Hmm.
And they distribute the heat throughout the pot.
So it's like I don't know, like a molecular conveyor belt, just constantly moving that heat energy around.
That's a great way to put it.
Cool. And this happens in other places too, right? Not just boiling water.
Oh, yeah. Convection is happening all around us.
Okay, give me an example.
Well, think about the weather.
Okay.
Convection currents in the atmosphere, they drive the wind and all those weather patterns.
Wow. Okay.
And then even deeper, under the Earth's surface, convection currents are moving magma around,
Oh, wow.
leading to volcanoes and earthquakes and all that.
So these invisible forces are shaping our planet. That's incredible.
It's pretty mind-blowing when you think about it.
It really is.
Mm.
Okay, so conduction is direct contact. Convection is these flows of hot and cold,
Mm.
and then there's radiation. And that one always seemed a bit different to me because it doesn't need anything to, like, travel through.
Right. Radiation is unique because it doesn't need a medium. It can travel through the vacuum of space,
Mm-hmm.
which is how we get heat from the sun.
It's like a wireless transmission of heat energy.
Exactly. And it happens through electromagnetic waves,
Electromagnetic waves, okay.
just like light and radio waves.
So everything is giving off this radiation.
Yeah, pretty much. Every object emits some amount of thermal radiation.
Okay.
And the hotter the object, the more radiation it emits.
So, like, even our bodies are giving off radiation right now.
Yep, we're emitting infrared radiation. That's how those thermal cameras work.
Oh, that's right. They can see our body heat.
Yeah, and then really hot objects, like the sun, they emit a much wider range of radiation, including visible light,
So the sun is just this massive radiation furnace,
basically.
just blasting us with energy across millions of miles.
Keeps us warm, though.
It does. It does.
Keeps the plants growing.
Yeah. Radiation's pretty important.
It is. It's how we get warmth from a fireplace. It's involved in all sorts of technology.
Wow. We've covered so much ground in this deep dive. From just touching a hot object to absolute zero to these different ways heat can move around. It's incredible how much there is to learn about something that feels so simple, you know?
Right. It really shows the power of science. Like by asking questions and making observations, we can uncover all these amazing things about the world around us.
And it's not just about satisfying our curiosity.
Oh.
This knowledge helps us build new technologies and solve problems and just, I don't know, appreciate the universe in a whole new way.
Absolutely.
So the next time I'm out in the sun or feeling that cold winter air, I'm going to be thinking about those dancing molecules and the energy flowing all around.
Yeah, there's a whole universe of wonder hidden in plain sight.
That's a great way to put it. Well, on that note, I think we've reached the end of our deep dive into heat and temperature.
I think so. We've explored a lot.
I hope everyone listening has enjoyed the journey as much as I have.
Yeah, thanks for joining us on the deep dive.
And until next time, keep those minds curious and those molecules moving.